Jay? Yeah, Jay Sheffield. Okay. Okay. All right. Let's start from the current slide. I don't think we got anything started here before. And, okay. We're still in chapter, well, let's hit a couple of announcements first. I don't know of too many for this week. I do know that Friday there's a presentation at the A.G. Gaston Auditorium on the Birmingham East Campus. Can I get your name, please? Thank you. Michaela, got it. And, oh, got it. Undo it. Okay. Anyone else come in since the called roll? Okay. There is a presentation, I think, by UAB Theater on the Taming of the Shrew, which is a Shakespearean play, but of course they turned it around, and it was a story of a guy trying to tame his fiancée or wife or whatever, and it's a comedy, and UAB has decided to produce it where the woman's trying to tame the man. So they say it should be quite funny, but you can check the boards. I think it's Friday at 10 on the Birmingham East Campus, A.G. Gaston Auditorium. Name, please? Webster, got it. Jayla. Oh, I'm on the wrong page. All right, and the key there. I gotta find you. Oops. There you go. Okay. Anyone else come in since the called roll? Okay, those are the major things I know about. I think I said this to you before, but in case all of you didn't hear it, several weeks ago I asked the Cengage WebAssign people to set up the class and to put something out there. They finally did like a week ago, though it had been weeks ago that I asked them to do it. They finally got it done, but they only did it, I think, for this class. I asked them to do it both for this class, Math 112 and 113. I've got to see why they didn't do it for the other classes as well. But it's out there. If you check Blackboard, there's an announcement. I think it went out as an email as well. I don't know. I don't get your emails, but it gives you the procedures to access WebAssign. I'm not going to make any assignments on it, but you may find the tutorials and things like that. To me, that's the only thing worthwhile about WebAssign is they do have decent tutorials and things like that. So, and they probably put some exercises out there that you can practice on. So knock yourself out with that. But the tutorial should be quite good. All right. Other things, and this is why I keep turning back the page, and every time I do, someone else walks in. 2 people have not turned in the first quiz. One of them has not paid, so I have a feeling she's no longer in the class. The other one hasn't been here for now, this is the 4th week. So I have a feeling she's not going to continue in the class, but I don't know that for sure. As soon as I can find out something, I'd like to get those quizzes back to you. They're all graded. If you need to see your grade, you can see your grade on Blackboard, but you can see the actual quiz. Now the test, those same 2 people plus 1, 2, 3, 4, 5, 6 more either haven't taken it or haven't finished it, or I couldn't tell if you had finished it. So if you don't see a grade for test 1 on Blackboard, that means I wasn't sure if you were through or not. If you're through, let me know. I've got it marked, graded, and everything, but I just wasn't sure you were through with the test. Or if you see a grade out there and say, I wasn't through, let me know that too. I can easily change the grade. But please let me know. I'd like to get those back to you as soon as possible too. All right, any questions on anything we've covered so far? All right, we're in Chapter 4, Rational Expressions. We're now moved to 4.23, Adding and Subtracting Rational Expressions. We did multiplication and division. Those, believe it or not, are easier than adding and subtracting, though adding and subtracting isn't that hard either. So what our procedure here, objectives are to add and subtract rational numbers. That's just a review, and then we'll move that whole process into adding and subtracting rational expressions. Now remind me, what's a rational expression? Say again? I hear something, but I can't make it out. Rational expression. What's a rational expression? And we've been doing it for about a week or two now. What's a rational expression? What's a fraction? Say again? A fraction, fractional form. What's now a fraction is with a number in the numerator or denominator. What's a rational expression? What's it got in numerator or denominator? Polynomial. Polynomials. Is this CJ, right? Yeah. Okay, and JT? Okay. Yeah. Flipping the page. JT's here and CJ's here. All right. Good deal. So that's the second thing we'll do in this section, add and subtract rational expressions. Okay, let's go back to the numbers. Even though it says adding and subtracting rational expressions, we're going to deal with numbers first. We can define the addition and subtraction of rational numbers. They're also called rational numbers, fractions, as follows. Okay, A, B, and C are all integers. Okay, with one exception, B cannot be 0. Any integer other than 0. Why? Because B shows up in the denominator. You can never divide by 0. Okay? So A and B can be any integers, A and C, any integers, B, any integer except 0. Now, how we define addition and subtraction of rational numbers or fractions, A over B plus C over B. You're adding two fractional forms, same denominator, add the numerators, keep the denominator. And it kind of makes sense. If you're adding 3 apples to 4 apples, you'd have 7 apples. If you're adding 3 twelfths to 4 twelfths, you have 7 twelfths. Just think about it that same way. It's exactly what we're doing with fractions. If you have the same denominator, add the numerators, keep the denominator. If, and subtraction is the same thing, if you have two fractional forms, subtracting the two, if they have the same denominators, keep the denominator, subtract the numerators. It's just pretty straightforward, okay? We can add and subtract rational numbers with a common denominator by adding or subtracting the numerators, placing the result over that common denominator. You're used to that. You've done it your whole mathematical lives almost, ever since you got into fractions. So let's look at a few and see what we can do. 2 ninths plus 3 ninths. 5 ninths. 7 eighths minus 3 eighths. 4 eighths, which is? Say again? 1/2, exactly. How about 4 sixths plus a negative 5 sixths? Negative 1 sixth. Perfect, okay? And 7 tenths minus, plus a 4 over negative 10. Say again? Okay, it's not 0, it's 10. Negative 10. No, you don't add the denominator. You keep the denominator. First thing you do here is move the decimal either here or there, or change that plus to a minus. When you have just one negative sign, move that to put it out front or in the numerator. Now you have the same denominator, but you don't mess with your denominators except maybe moving that sign. So that would give you 7 tenths minus 4 tenths, or plus a negative 4 tenths. They moved it that way. And what would that give you? 3 tenths. Got it. All right. Now, don't ever mess around with the denominators like adding them. You don't do that. You only add numerators if you have common denominators. You're absolutely right. These are not the same denominators. So what you have to do is move the minus sign either up here or here. Just when you have an odd number of minus signs, get it into a more convenient place. Not down there, put it here or here. They moved it here. And then you have common denominators. 7 plus negative 4 is 3. All right. Now, how about if we put some expressions there? 3 over x plus 9 over x. We can use the same common denominator approach when adding or subtracting rational expressions as these show, okay? So 3 over x plus 9 over x. 12 over x, exactly. 8 over x minus 2 minus 3 over x minus 2. 5 over x minus 2. Add or subtract the numerators, keep the denominators. 9 over 4y plus 5 over 4y. 14 over 4y. But 14 over 4y can be reduced. How? 7 over 2y. Always simplify your answers as far as you can. Okay? Don't forget to simplify the final answer. Okay? Now, if all fractions were always same denominator, this would be easier than multiplying and dividing, wouldn't it? Piece of cake, right? Except guess what? Life is not always that neat. Quite often you have denominators that aren't the same. Here's a few more that are. So let's see what we got here. N squared over n minus 1 minus 1 over n minus 1. What do you get? N squared minus 1, right? N squared minus 1 over n minus 1, right? Okay, say that again.
N squared minus 1 is going to give you 1 n, right? So it would be 1 over n minus 1 or n over n minus 1.
No, it's n squared minus 1. You don't subtract 1 from n squared. They're not like terms. You subtract them, but you can't eliminate anything. N squared minus 1 over n minus 1, right? Okay? Now, what can you do with that? Second? Yes, factor that to be n plus 1 times n minus 1. N minus 1's go out, and your answer is n plus 1. Now, perhaps I should have been saying this all along, but I haven't because the book hasn't said it. But really, in real life, when you have a problem like this, whether you write it down or not, you should always think to yourself when you read this, n can't be 1, right? Because if n were 1, your denominator would be 0. You can't ever divide by 0. So n can't be 1 here, n can't be 1 there. Now, that's your final answer. You look at that and say n plus 1. It doesn't look like there's any problem in the world with n being 1. Because 1 plus 1 is 2. That's a perfectly good sounding answer. Except it can't happen, because if it can't happen back here, it can't happen over there. So in reality, the book is going to say this. We will not always write that down, but you should think it. N can't be 1. Sort of a minor thing, but it is something to think about. What do we have here? 6a squared over 2a plus 1 plus 13a plus 5 over 2a plus 1. What does that produce?
6a squared plus 13a plus 5 over 2a plus 1.
Excellent. Now what might you do with that? Say again? Factor, absolutely. Let's see if we can factor. Let me get your name, please. Minuet, got it. And? Huh? Chris, got it. Okay, I know you're in here. Quit hiding. There you are. Okay. Now, what we had here was a 6a squared plus 13a plus 5. Okay? Now, I'm really hoping that has a factor of, this is on page 196, yeah. So let's fiddle with that a little bit. All right? We're hoping that this factors. Now, doesn't have to factor this way, but if I'm hoping anyway, why not just hope that 2a plus 1 is a potential factor, right? That would make things simpler. If it's not, we don't need to factor anyway. Well, 2a will go into 6a squared, so it might. 1 will go into 5, it might. The signs are right, so let's try it. Let's try 2a plus 1 to be one of those factors. Okay? Now, if 2a plus 1, wait a minute, one of the factors, not both factors, where is my brain this morning? Okay? All right. 2a plus 1 is one of the factors. Now, if 2a plus 1 is a factor, what must this other first term be? 2a starts here, 6a squared here, what must this be? 3a. Okay? So we'll put a 3a there. All right? What sign? Plus. And what would have to be the last term? 5, exactly. Now, that's not guaranteed to work. You have to check it and make sure it works. 2a times 3a is 6a squared. That works. 2a times 5 is 10a. Plus 3a is 13a. Ha! That works too. And 1 times 5 is 5. Yes, that works. And now what can we do? Divide out the 2a plus 1, which they did too, and gave us 3a plus 5. Now, and again, they don't require you to write this down, but after a while, you should be thinking, a can't be negative 1/2. Because if a were negative 1/2, 2 times negative 1/2 would be a minus 1 plus 1 is 0. Can't happen. You can't do it. So therefore, you should really write that over there. It doesn't look like a equals negative 1/2 would be any problem at all for your final answer, and it wouldn't be, except it won't work in the problem to begin with. So, just a minor point. In each of the previous examples that involve rational expressions, this is what they're saying, we should technically restrict the variables to exclude division by 0. Okay? For something like this that we did earlier, 3 over x plus 9 over x is equal to 12 over x. That's true as long as x is not equal to 0. Well, that's obvious in your answer as well as in the original problem. Okay? This one, and those two, both of them, are not obvious in your answers because it's not obvious that n can't be a 1 by your answer, but only in your original problem. So you really should say it, however the book is going. Most of the time, leave that out. And this is what they say here. Likewise, that would be 8 over x minus 2. This is one we did earlier. Over x minus 3 over x minus 2 is 5 over x minus 2, as long as x doesn't equal 2. Well, you can see that in your answer as well as the problem is when you can't see it in the answer, you still should have done that. But rather than taking the time and space to write down restrictions for each problem, we will merely assume that such restrictions exist. If rational numbers do not have a... That should be a new slide right there, okay? So we're just going to assume that it works for all the values we need it to. And we're not going to use those that it wouldn't, okay? That's what the book says. Now here's a whole new ballgame. If rational numbers, this is what I was saying before, that do not have a common denominator are to be added or subtracted, can we do anything?
No.
Sure. What do we do? Make them have common denominators. How do we do that? Find the blank common denominator. Least common denominator, of course, okay? Then we apply this fundamental principle of fractions that if you have A over B and something else was a 7 over K, B and K are not the same, so multiply by whatever it takes to make both denominators the same. Multiply this one by K, 7 over K multiplied by B over B, you got it. Now why can we do that? Why can we multiply the denominator by K? Because we also multiply the numerator by K. What's K over K? No. 1. 3 over 3 is 1. 7 over 7 is 1. K over K is 1. K can't be 0, by the way. Don't ever go around multiplying numerator and denominator by 0. You're going to screw up the whole problem then. But any non-zero number, you can multiply numerator and denominator by that same number. That gives you what they call equivalent fractions with a common denominator. Now, you don't see the common denominator there, but that's the goal. Okay? So, here's sort of their example. Equivalent fractions are fractions such as 1/2 and how many fourths? Equivalent fraction. 2/4, of course. I think in terms of food, okay? If I have half a pie, that's the same as 2/4 of a pie. Cut that pie into fourths, I eat two of those, I'm still eating half a pie. Okay, so that's what you think of. How do we get from here to here? Multiply by? No. Yeah, multiply by 1. 2 over 2. 1 times 2 is 2. 2 times 2 is 4. You got it. They name the same number. They are the same value. Okay? So what would we do here? 1/2 plus 1/3. Say again? I can't hear.
3 over 6.
Okay. You doing this on your calculator?
No.
Good. Okay. But how do we do it in our heads? Okay. What do we look for? Common denominators. You can't add things with different denominators, so you have to get the same denominator. What's a number that both 2 will go into and 3 will go into? 6. 24, they also work, but you go for the least common denominator, 6. Okay? How many 6 is 1/2? How many 6 is 1/2? In other words, what you have to multiply the 2 by to make it a 6? 3, so you multiply the numerator by 3. That would be 3/6. How many 6 is 1/3? 2/6. Multiply the denominator by 2 and the numerator by 2. And what's 3/6 plus 2/6? 5/6, exactly. Okay? So that's what we do. First, get your denominators being the same. You do that by building the fractions. Before this, we always reduced our final answer to simplest form. Now we build the fraction and have common denominators. Okay? 1/2 and 3/6 are equivalent. 1/3 and 2/6 are equivalent. Note that we chose 6 as the common denominator. The 6 is the least common multiple of the original denominators 2 and 3. Okay? Certainly, many other numbers are common, but we want to get the ones that are smallest, so we don't have to worry about reducing at the end as much. Okay? So the least common multiple of a set of whole numbers is the smallest non-zero whole number divisible by each of the other numbers. In general, we use the least common multiple of the denominator of the fractions to be added or subtracted and call that the least common denominator. That's what we always usually call it. They like to call it least common multiple of the denominators, but much shorter to say least common denominator. A least common denominator may be found by inspection or by using prime factorization of the denominators. And I'm sure they're going to show you one that will require that. Okay, here's what we got. Perform the indicated operations. 3/5 plus 1/6 minus 13/15. Oh boy, this is one of those not real clear how to add those, is it? What do we have to get first? It's a minus, not an equal sign. What do we have to get first? Oh, all right. Okay. What do we need to do first? Say again? I can't hear you.
Times 305 minus 6 over 6.
Multiply by 6 over 6? Okay, why did you choose 6? Because it is your least common denominator. Okay? Notice this has a 5. This is a 2 times 3. This is a 3 times 5. So what's your least common denominator? It's got to have the 2, the 3, and the 5. And 2 times 3, 6 times 5 is 30. So, say again? You're lost. Okay? Before we can add or subtract those things, we have to have a common denominator, right? So, let's break it down. 5 is just 5 times 1. That's a prime number. 6 is 2 times 3, right? And 15 is what? 3 times 5, okay? Now we have to have a common denominator, and we already have a 3 here, a 1 here, and a 13 up here, okay? Now we need to get the same denominators, okay? So all 3 of these denominators have to have a factor of 2, right? This one already does, so we need to get a 2 in this one, but if we put it there, we've got to put it up there, right? Okay, and we need to put 1 here, a 2 here, but if we do that, we've got to have a 2 up here as well, right? Okay, now, we've got a 2 times 5 times 2, and a 2 times 3, and a 2 times 3 times 5. Well, what else do we need here? We need a 3. So let's multiply everything by 3. Numerator and denominator. And for the second one, a 5. So let's multiply by a 5 here. But if you do that, you have to do a 5 up there as well, right? Those are multiplied, okay? So what's 2 times 3 times 5? Say again? 30. So your least common denominator is 30. Okay, let's multiply these together. 3 times 3 times 2 is 18. 1 times 5 is 5. And 2 times 13 is 26. Okay, let's add the positives. 18 plus 5 is 23 thirtieths. Minus 26 thirtieths would be what? Negative 3 thirtieths. Are we through? Say again? Simplifying, that would be negative 1 over 10. Very good. Excellent. Now that's sort of the long way to do it, but if that helps you see it, do it that way. Okay? You've got to have the same denominators, so if you do your prime factorization, multiply whatever it takes to get that same common denominator. But if you multiply the denominator, you've got to multiply the numerator as well. Now, all right. Let's see how they did it. Let me erase that. Any questions before I erase this? Do you see it? Any other questions? All right. Let's see how they do it. Again, by inspection, they say we can determine the least common denominator is 30. Now, how do they inspect that and see? Here's another way to do it. This is kind of how I do it if it doesn't get too complicated. I'll first look at the biggest denominator. Will 5 go into 15? Yes. But will 6 go into 15? No. So, what I'm going to do is double 15. Okay? That makes it a 30. Will 5 go into 30? Yes. Will 6 go into 30? Yes. Will 15 go into 30? Sure. Okay? So So that's one way you can do it, okay? But sometimes they're so far apart and so far off, that's really complicated. But that's how you do it. So what they did then, they determined ahead of time, they said by inspection, the least common denominator is 30. So then they say, with this 3/5, what can I multiply that 5 by to make it 30? 6. So, but if you multiply by 6, the denominator by 6, you multiply the numerator by 6, because 6 over 6 is 1. And when can you multiply by 1? Anytime you want to. It doesn't change the value at all. Okay? Then you want this 6 to become a 30. What do you need to multiply the 6 by to make it a 30? 5. But if you multiply the denominator by 5, multiply the numerator by 5. Okay? And then to get the 15 to become 30, you multiply by 2. If you multiply the denominator by 2, multiply the numerator by 2 as well. Okay? Same thing we did, only it looks different. Okay? This would be 18/30 plus 5/30 minus 26/30. That's exactly the same numbers we got before. 18/30 plus 5/30 minus 26/30. That would be, goodness gracious, they stringed this out. 18 plus 5 minus 26 over 30, which would be negative 3 over 30, which would also be negative 1/10. Don't forget to reduce, they say. All right, does that make sense? That, unfortunately, was example 2. We wound up skipping example 1, didn't we? Let's go back and do example 1. Why did they skip example 1? I wasn't paying attention. Here we have 5/6 minus 3/8. Now, there's several ways you can approach this. How would you like to approach it? Second? And what would be your least common denominator? Second? Okay. Okay. 2 goes into each of them, but what we want is the denominator each of these goes into. So certainly a 2's got to be there. 2's already there. So this is a factor that. 2 times 6. 2 times what? 3. And 8 is 2 times 4. Okay? So obviously you need another 2 over, and by the way, you need another 4 here, so multiply that by 4 and multiply this by 3. That's, okay, let's go back. That will give you a common denominator. It won't be the least common denominator, though. Okay? Here's what we do. Here's what I would suggest doing. Let's make this 4 a 2 times 2. Okay? So, yeah, I think I was right before. This has to have 3 2's and a 3. Yeah, that's right. 3 2's and a 3. Well, what do we have? We multiply this one by 4, and we multiply this one by 3. Okay? 5 times 4 and 3 times 3. Okay. Shot, right? Okay. All right. I haven't done this. I mean, I see it. I'm not sure you would see it. Let's back off and start this over, right? Okay. All right. Let's do it the way we did before. You don't have to do it this way, but if you don't see that least common denominator right at the beginning, this will work. Okay? This will be a 2 times 3, and this will be a 2 times 2 times 2. Okay? This already had a 5 here and had a 3 here. So, what do we need? What's going to be our least common denominator? You've got 1, 2 already here, but you need 2 more over here, and you need a 3 over there, right? You see that? To make them a common denominator, you got to multiply this by 2 more 2's and multiply this by 1 3. You see that? This, by the way, is example 1, top of page 197. So you're going to have to multiply this by 2 times 2. That means you multiply this by 2 times 2. This one you got to multiply by 3, multiply this by 3. Okay? Does that make sense? You've got to have the denominators the same. Anything you multiply this by to make it look like that, you've got to multiply that by the same thing. So this had a 2 times 3, this had a 2 times 2 times 2. You already got 1 2, you need 2 more 2's here and 1 3 over here. Right? So multiply this by 2 2's and this by 1 3. And now what do you have? What's 2 times 2 times 5? 20. What's your denominator? 8 times 3 is 24. Minus 3 times 3, 9 over 24. And what does that give you? 11 over 24. You got it. And that's what they got to. Now, they did it, quote, by inspection. So let's go back to my second way of doing it. Pick the largest denominator, 8. 6 won't go into 8, right? Double 8, that would be 16. 6 won't go into 16. So triple 8. 3 times 8 would be 24. 6 will go into 24, 8 will go into 24, you can do it that way too. Now that's my method of doing. Most of the time the books don't teach that, but it seems to work. Okay? But you check every time to see if you've got your least common denominator. And if you did it that way and went straight to the 24s, okay, and you said the least common neighbor is 24, okay, if you had already decided that, then here's another way. 6 will go into 24. 4 times 5 is 20. This is how I learned it back when I was very young, and I didn't know why we were doing it, but I knew it worked. Okay, this is why it works. And then 8 will go into 24. 3 times 3 times 3 is 9. Okay, and that gave you the same result, 11 24. Okay, you've got to have the same denominators, and they've got to have all of the same factors. Okay, so a couple of ways to do that. Let's move on to example 3. Are there any questions there? Any questions before we move on? Okay. Okay, that was example 2. All right, obviously they don't do example 3 either. So let's go back and do example 3. Add 7/18 plus 11 24. Now this one gets up into pretty big numbers pretty quick. In fact, it starts with pretty big numbers. So doubling these and tripling them and stuff, that may be a little harder to do. So which way you want to do it? You tell me. Want to do prime factorization or something else? You tell me how you want to approach it. Help me. Prime factorization. All right, so let's do the prime factorization of 18. What's the smallest prime number will go into 18? What's the smallest prime number? 2. 2 will go in 18 how many times? 9. What's the smallest prime number will go into 9? 3. 3 times what? 3. Both of those are prime. So we got our first one, prime factor. Okay, how about the second? Smallest prime number going to 24. 2. 2 times what? 12. What's the smallest prime number going to 12? 2. Okay, 2 times what? 6. What's the smallest prime number going to 6? 2 times what? 3. Okay, there's our prime factorization of that. Does that make sense? Okay. Now, I always like to check and make sure I didn't make a mistake. This is 9 times 2 is 18. This is 8 times 3 is 24. Yes, those are right. Now, what do I need to multiply this by to get it to look something like this? At least what? See, this has 1, 2. I need 3 2s. To multiply this by, oh, let me go and write my numerators in. This is a 7 up here and 11 here. Okay? Now, this has 3 2s, this only has 1, so I have to multiply by 2 more 2s. So let's multiply times 2 times 2. Okay, well, what's 2 times 2? Okay, let's multiply the numerator by 4 as well. Okay, now, I've got this one looking like this. What do I have to multiply this by to make it look like this? A 3. Okay, so let's multiply that by a 3. So what would I have to multiply the numerator by? 3. Very good. What's 4 times 7? 28 plus 33 over, and that's 8 times 9 is what? 72? Is that right? And what's 28 plus 33? 61 70 seconds. And 61, by the way, is a prime number, so you know you can't factor that any further. Right? Make sense? You see how to do that? See, doing my other way, taking the biggest number, 18 won't go to 24, you double that, and that would be 48. 18 won't go to 48. Triple 24, and you've got 72. Yeah, you could get there like that, but it takes a while. And then does 18 go to 72? I don't know that for sure, but get my calculator down. Yes, it does. So yeah, we could do it that way. Huh? Yeah, 4 times, exactly. So, you could do it that way. Either way works. Do whatever makes the most sense to you. Okay? Any questions on that? Let's see how the book did. 61 70 seconds. Good for them. Okay? Whoa, they skip example 4 too. So let's do example 4. Okay? X plus 2 over 4 plus 3x plus 1 over 3. How can we even do that? Can we add those two? Sure we can. How? Got to make the denominators the same. What do you think the common denominator would be? 12. Very good. He did that by inspection. Okay. Now, what did you have to multiply this denominator here, 4 by, to get 12? 3. Okay. Let's do that up here. If we multiply the denominator by 3, what did you better multiply the numerator by? 3 as well. Okay. Over here, what do we have to multiply that denominator by to make it 12? 4. If you multiply the denominator by 4, you better multiply the numerator by 4 as well, right? Okay? Let's distribute that. 3 times x is 3x. Second, plus 6, plus over here, 12x, plus 4. Okay, let's add those together. Now that we have the same denominators, you can write it all over that denominator and add your numerators. 3x with 12x's, 15x plus 10. Okay? Now, I look at that. Does everybody see that? Okay, any questions? All right, I'll look at that and say, hey, I can factor this, can I? What's common factor? 5. 5 times 3x plus 2. But you know, 5 won't go into 12, so there's no reason to. I mean, always check and see if you can, but what I can factor out there, it's not going to help me. So you can leave it just like this, or you can factor it. It doesn't hurt to factor it. Just a little extra work, and I'm really lazy, okay? So I don't do any extra work that I don't have to, okay? So that's a perfectly good answer. Let's see what they got. 15x plus 10 over 12. Good for them. Any questions on that? They talk about factoring that too, so you can read that if you'd like. Any questions? Okay. Let's go to... And by the way, folks, every one of these examples has a little classroom example off to the left that would be a great thing to do as soon as you can. If you have a free period right after this, go home or go to the library, go to a classroom somewhere, do as many of those classroom examples as you can, what we've covered today. While it's fresh on your mind, do them. That makes it yours, okay? And if you got another class right after this, as soon as you have free time, try to do those, okay? So let's erase that ink and go to this one. A minus 2 over 2 minus A minus 6 over 6. What would be your first step? And what's the least common denominator? 6. How do we get this 2 to become a 6? Multiply it by 3, but if you multiply the denominator by 3, what did you better do? By the numerator by 3 as well. Okay? What's our new numerator now? 3a minus 6 over 6, right? Minus a minus 6 over 6. Now be careful, people. When you have a minus sign here, you have to change the signs of everything in that numerator and make it a plus. In order to subtract things, you have to change signs and add. So let's do that. Rules of subtracting sign numbers. Your least common denominator is 6, and this becomes a 3a minus 6, and then you have a minus a minus 6, okay? I'm doing an extra step there just to point this out. This will be 3a minus 6, and when you distribute the minus sign there, what does that become? Minus times a plus is minus a plus 6 over 6, right? Are you with me? Say again? Okay. Okay. There's two ways to do it. I'm showing you the what may look like the obvious way minus this. Okay. So I did that. So I put that in parentheses. Now, if you did it in one step, here's what I would do: minus a minus a minus 6 is plus 6. You can go straight from here to there if you want to, but if you tend to make sign errors easily, do this to eliminate that. But you don't just change this sign, you change both signs here. That's why it becomes a minus a plus 6. So should it be plus a plus 6? Where are you talking about? Oh, you mean your final answer?
No, you said you changed that sign in the middle. You still on the other side.
Okay, you change. This was a positive a here, right? Okay.
I'm talking about that minus sign right there in the middle between both. Yeah. You still got it down there. You said you changed it.
Okay. Well, what I said, you're going to have to, and I showed you why you have to. Because this is minus times this. That changes this sign to a minus, and that sign to a plus. I did it here, but I showed you why, because if you put it in front of that, it makes it obvious you got it. Huh? I changed it here. Look at this. It changed this to a minus and that to a plus.
Oh. You changed the A.
Oh, okay.
Yeah, you have to. That's why I said you have to change them both. That's why I put this step in here. The minus times this thing, minus times that thing, and then you see that changes that to a minus and that to a plus.
Oh, okay.
Right, exactly. All right, what does that become now? 3a minus a is 2a, and minus 6 plus 6 is 0. Okay, over 6. Are you through? Say it again? Yes, that would be a over 3. Perfect. Reduce, always reduce. Don't forget to. A over 3, that's what they got. Okay. You know, I think they did that one. Wait, let me see. I'm sorry. I did it on the wrong. No, they didn't. Okay. Now, here. To add and subtract rational expressions with different denominators, follow the same basic routine you follow when you add or subtract rational numbers with different denominators. What do? Factor everything inside. Well, factor the denominators anyway. Factor those denominators just like we did, and then find the least common denominators. Okay? So that's going to lead to example 6. No, it isn't. No, it does. Okay. Yeah. I don't know why they had the previous expression. We haven't gotten there yet. Let's do this operation. What do we do first? Okay, what's going to be your least common denominator? Can you see it right off the top? I have to do a lot of head scratching. And since I don't have much to scratch, hey, not that funny. Okay. Now, what I think I'll do is factor those denominators. Oh, look at that. Very good. Everybody see that? Or you want to see how we got it? Huh? How we got it? What's 10? Factor that. 2 times 5. That's the prime factorization. 15. 3 times 5. Prime factorization. 18. Say again? 9 and 2, and 9 is 3 times 3. Okay, there's the prime factorization. Right? Everybody see it? All right, what are we going to need to do having this one? What's going to be our least common denominators that got to have all those factors in it? Well, it's 1, 2, 2 3s, and 1 5, right? 1, 2, 2. I can't talk and write something different. Okay. All right. 1, 2 times 2 3s. The old gray cells ain't what they used to be. Okay. And 1 5. Right? 1 2 2 2 3s and 1 5. 1 2 2 3s and 1 5. That's ugly, I'm sorry. You see that's your least common denominator. You got a 2 here, no 2's here, a 2 here, you gotta have a 2. You got no 3's here, 1 3 here, 2 3's there. You gotta have 2 3's. Okay? You got a 5 here, a 5 here, no 5's, you gotta have a 5 in all 3. Okay? Now, that's your least common denominator. If you can read it. What did you have to multiply this by to get this? what do you have to multiply this denominator by to make it equal that? 9. So do a 9 times x plus 3, right? Now what did you have to multiply this by to make that? 10. So that'll be a 10 here times, whoa. So again? 15. Okay, you make up your mind here. Okay, let's see. No, it's not 10. You have to get this to get, it's 6, right? That's what you, why didn't you say 6, huh? All right. All right, so that's going to be a 6. Okay. 6 times 2x plus 1, right? And what did you have to multiply this one by to get that? 5. So that'll be a 5 times x minus 2, right? So multiply those out for me. 9x plus 27 plus 12x plus 6 minus 5x plus 10. All right, very good. Oops, I left off my plus sign, which is pretty important. Okay? All right. Now, I'd say take one more step here, folks. 9x plus 27 over, can we go on and multiply that out? That'd be 90. Didn't you say that early on? Yeah, very good. Plus 12x plus 6 over 90 minus, okay? Yeah, make that a plus negative 5x minus 10. If you change the minus to a plus, change the signs of both of those. And that will be over 90. You see what I did there? I took this minus sign here, made it a plus, and changed signs of both of these. Like we did before, right? Okay? So, now let's combine like terms. 9x plus 12x is 21x minus 5x is 16x. 27 plus 6 is 33 minus 10 plus 23 over 90. And look at that, as much as you would like, I do not think that you can reduce that any further. So there's our answer. You see how that works? All right. Let's clear, if there are no questions, clear this and see how they did it. Okay? First thing they did, if you cannot determine the LCD, the least common denominator by inspection, then use the prime factored forms, which is what we did. Noticing there that it must contain one factor of 2, 2 factors of 3, and 1 factor of 5, and that's going to be a 90, just like Chuck said right early on. Okay? So then, what you had to do to get the first one, the denominator being 90, is multiply by 9 over 9. The second one you had to multiply by 6 over 6. And the third one you had to multiply by 5 over 5. So we saw how we got that. And when they multiply, I don't like the way they wrote it, but yeah, now they write it down a different way. 9 times x plus 3, that's how we went right there. Plus 6 times x, 2x plus 1, minus 5 times x minus 2. Okay? Now, then this is a pretty good way to do it. 9 times x is 9x. Well, they wrote it out here again. But what they did was pull the minus up with the 5 times x plus 2. That's a good way to do it. That helps you eliminate sign errors. Okay? And let's see what they got then. 9x plus 27 plus 12x plus 6 minus 5x plus 10. Okay? Over 90. And that would be 16x plus 43. Is that what we got? I must have made an error there somewhere, didn't I? I think I know what I did.
That 10 was negative 10.
Yeah. I lost it. Yeah, I erased it off. I'm sorry, I botched it up. This is the correct way. Do that minus 5 times x minus 2. I think I put a plus 10, a minus 10, and it should have been a plus 10. See, those signs will sneak up and bite you where you don't want it to be bit, okay? So watch out for them. I think I had written x plus 2, and it should have been x minus 2. I think that was my error, okay? But you got 10x, or 16x plus 43 over 90. Nothing will reduce, so you got that done. All right. Whoa. They're skipping example 7. Let's see if we can get example 7 done real quickly here. Okay? Add 3 over 2x, and make sure I write it down right this time, plus 5 over 3y. Whoa, a little bit different this one, isn't it? Because now we don't just have numbers in the denominator, we have variables as well. But we do it the same way. What's our least common denominator between those two denominators? 6 x y. 6 x y. Okay? How many times will 2x go into 6xy? 3y times, right? So that's going to be 3 times 3y plus, how many times will 3y go into 6xy? 2x times. So it'll be 2x times 5, or 5 times 2x. Okay? What's that first numerator become? Help me. 9y plus 10x over 6xy. Anything you can do to simplify? No. Okay? You'd have to be able to factor something out here. There's nothing to factor. This is 3 times 3 times y, 2 times 5 times x. Nothing in common. That's a perfectly correct, legitimate, simplified form. Okay? Think we can squeeze one more in? Sure we can. Okay? All right. Let's do 7 over 12ab minus 11 over 15 a squared. Might need to do a prime factorization, might we? 12 is what? 2 times, say again? 2 times 3 times A times B. Okay? What's the 15? 3 times 5 times A times A. So what's going to be our least common denominator here? You got to have 2 2's, right? 2 times 2. You got to have 1 3. 3. Got to have 1 5. That's 5. Got to have 2 A's. That's A times A. And you got to have 1 B. There's your least common denominator. Right? Okay. What did you have to multiply this denominator by to get that one? Well, there's your that. And there's that. So you had to multiply by 5a. So this is 7 times 5a. Let's put it over here. 7 times 5a. That's really not a good place to put it here. Just leave a 7 here and 11 there. Okay. Minus 11. Now, what did you have to multiply this by to get this over here? 4b. Okay. I'm going to take your word for it now if I can get to my pen. Okay. 4b. Let's see. 4b. You're right. Good. And what does this become? 35a minus 44B, all divided by, what does this come out to? That's 20, that's 60 A squared B. Is that right? Anything you can do to simplify that? I think not. 35A minus 44B over 60A squared B. That means we will start next time with example 9. We almost finished the section, came so close. We got 2 more to go. Huh? That we ended on page 199. Homework, okay? Don't want you to miss this. Do any of the odds 1 through 11? Do any of the odds 13 through 65? Well, at least through... Let's lose 47.
47.
Through 47. We'll do the rest next time. All right.
I have a question.
Yes.
We have a quiz.
Yeah, I didn't have a copy, but I'll give it to you next time. Are you going to be here?
Mm-hmm.
Huh? On the first 3 sections of chapter 4. Or 1 through 4, 3.
Because I wasn't here last week.
Yeah. And
Okay.
did you finish your test? I can't remember.
Mm-hmm.
You did.
You got my grade.
Okay, good. All right.